This video will cover how to use one of the most common equations we encounter in biochemistry, which I guess I'll just show. That equation is delta G equals delta G naught prime plus RT log of Q. So we're going to ask sort of when do we use it, and then talk about the mechanics of using it throughout this video. So when would we use it would be in a situation like this one. So these are all real numbers for human muscle cells. So imagine that we crack open a muscle cell. We know that that cell can run the following reaction. Pyruvate plus NADH goes to lactate plus NAD+. This reaction is important in lactic acid fermentation, which is important in anaerobic metabolism. And we want to know, is the reaction going forward or backwards? Are we going from pyruvate to lactate, or are we going from lactate to pyruvate? When we're, say, looking at a cell, maybe all we can measure are the concentrations of things. So we know the concentrations of pyruvate, NADH, lactate, and NAD+, but which way is favored? Like, which way is it going? To answer this question, we need to use the equation that I started with, this free energy equation. So what I'd like to do is I'm going to go through the terms really quickly, and then in a little bit more detail, and then how to use it. So okay, what are the terms? The first is the gas constant, R. I'm in kilojoules per mole, so that's 0.008314 kilojoules per mole Kelvin. Temperature in Kelvin depends on the system. For us, that's 310. Room temperature is 298 Kelvin. Then we have these other more mysterious terms maybe. There's delta G, which for this video I'm going to call the current distance from equilibrium. We've got delta G naught prime, which is the distance from equilibrium if all products and reactants are at 1 molar. And then Q, the ratio of products and reactants currently, or in this case, in the cell. What are they right now? And so I'm going to unpack these in a little bit more detail in a second if you're like, wait, that's too quick. So, okay, delta G. What is delta G? Delta G is the Gibbs free energy. What I like to think about it as is the relative probability of a forward or reverse reaction under the current conditions. So whatever the current state of the universe is, what's the relative probability of a forward or reverse? And I've shown this in previous videos, but basically this is a graph of delta G on this axis, so going from negative to positive. In the middle, we've got a delta G equals 0, and at the delta G equals 0, both the forward reaction and the reverse reaction are equally favorable. When you get a negative delta G, that's saying the forward reaction is favorable. We can bet that there'll be a forward reaction. And when you get down here, you're saying that the reverse reaction will be favorable. And in a sense, what we're trying to do is establish where are we on this scale? Are we strongly favoring reactant? Are we strongly favoring product? Or are we somewhere in the middle? Okay, that's the delta G. Delta G naught prime is the standard state Gibbs free energy. And this is the relative probability of a forward or reverse reaction under standard conditions. Standard conditions are defined as 298 Kelvin, 1 atmosphere of pressure, pH of 7 and 55 molars water. So it's a little different than the standard state you might have encountered in normal chemistry classes, but this is what biologists and biochemists use. And what I think the way to think about this delta G is you're saying, what is the delta G when I set the products and reactants to 1 molar? I just say, this is the other part of the standard state definition. It's saying products and reactants are all 1 molar. So you set them to 1 molar, and then you say, how far out of equilibrium am I? Am I strongly betting going forward, meaning the reaction is intrinsically favorable? Or is it a positive delta G, which means the reaction is intrinsically unfavorable? And so I like thinking about it this way. This is a measure of what is the intrinsic favorability of the reaction. So all else being equal, which way will the reaction go? Finally, the reaction quotient is the relative concentrations of the product and reactant under current conditions. So in the cell, right at this moment, what are the concentrations? So the way that we write this out is in the following way. So here I'm showing a reaction, a hypothetical reaction. The little numbers here are the stoichiometries. And then these are the identities. So I've got A molecule, A moles of A in this reaction, B moles of B, C moles of C, etc. And then if we write out the equilibrium constant, or the Q for this, the reaction quotient, we would write this out as the products multiplied together, each raised to their stoichiometries. So big D, big E, little e, and then over the reactants raised to their stoichiometries. And these are all multiplied together. So this would be multiply the products, the concentrations of the products, multiply the concentrations of the reactants. That will be your reaction quotient. Okay, so again, delta G, current distance from equilibrium, delta G naught prime, distance from equilibrium of all products and reactants are 1 molar, and then Q is the ratio of the current products and reactants. Steps. Then what are the steps we would actually use to do one of these problems? We would write out Q given the reaction. We would look up or estimate delta G naught prime. This is something that you basically have to find from somewhere else. This is not something you can just make up or you can derive without other information. We plug the values in, and then we do some interpretation of those results. So yeah, let's do some quick rules, and then we'll do it for our specific example of lactate and pyruvate. So one of the key rules is to always use molar concentrations. This is the one I find trips students up the most because we usually talk about concentrations. We measure them in a cell in millimolar or micromolar or something, and then if you plug that into these equations, doesn't work. You have to leave them as molar, and that's actually because it's a pretty subtle reason, but it's because the standard state energy is actually defined at 1 molar. And if you're using 1 millimolar, you're actually having a mismatch in unit. You can be off by orders of magnitude in your answer. So, so just always put everything in molar concentration units. Second, always use Kelvin temperatures. Don't just randomly do Celsius temperatures or Fahrenheit temperatures because you'll get the wrong answer. That's because the gas constant is defined in terms of absolute temperature. Just think about it as a unit cancellation problem. The gas constant is in kilojoules per mole Kelvin. If you do kilojoules per mole Kelvin times Celsius, well, you just haven't made any progress. And finally, if a reaction involves waters or protons, you can basically generally ignore them. And that's because water is in excess. There's 55 molar water around. So the 1 water that you put in your reaction is going to be changing that water concentration. And there's buffers that keep the pH roughly the same. And so basically you can think about proton and water concentrations being effectively constant and not affecting the free energies. So, okay, so use molar, just rules. Use molar, use Kelvin, and ignore waters and protons in the reactions. Okay, cool. So now let's think about doing this, actually do this as a calculation. So here again is our reaction, pyruvate going to lactate using with NADH and NAD+. This is a cell and it's got the following concentrations of things. How do we calculate that as our free energy? Which direction is favored? So here again are our steps: write out Q, look up or estimate delta G naught prime, plug in values, and interpret the results. So let's just do it. So first, write out Q for the reaction. This is a good chance for you to actually pause and do it yourself if you'd like. So give you a chance to pause. Okay, I'm assuming you paused. Here's what I would say for Q. Q equals, I don't have a fill, just making sure that it's going to be the products over the reactants. So the products would be lactate times NAD plus over the reactants. So that would be pyruvate times NADH. Okay, so that is our Q. And it's really important that you define that correctly with the products of the reactants if you're going to get the right answer. Next thing we need to do is look up or estimate delta G naught prime. You can look this one up in a table, and so this one, it turns out, is minus 24.96 kilojoules per mole. So that's the delta G naught prime. What that's saying is that this reaction is very favorable. Like if we set pyruvate and lactate and NADH and NAD plus to 1 molar, so they all have the same concentration, and we let the system relax, it's going to relax towards the products, right? We're going to see an accumulation of lactate and NAD plus and a depletion of pyruvate and NADH. And then we plug in values, right? So we've got all these things here. And so I'm actually going to write it out in the interest of really making sure we're all, on the same page here. So delta G equals minus 24.96. That's in kilojoules per mole. Plus R, 0.008314. And I've defined my temperature here. We're doing this calculation at 298 Kelvin. 298 Kelvin times the natural log of the concentrations in Q. And what, quick memory thing, what did I say you had to use these concentrations as? Can't leave them in millimolar, have to turn them into molar, right? So let's do that. So then the lactate in molar is 1E minus 3. And I'm going to check these off so I don't keep track of them. The NADH is 3 millimolar, so 3E minus 3. And then the pyruvate is 0.05 E minus 3. And then the NADH is 0.03 E minus 3. Okay. So I plug those in, and so this is a plus, and then we've got this R times T times the natural log of that stuff. Okay, cool. Now, already looking at this, you might be saying, oh, I already noticed a pattern, and that is that these ones have much higher concentrations, the products and the reactants. Remember that this tends to favor forming products over reactants. So when I first look at this, I'm like, oh, this must be, this seems like it's getting towards equilibrium. That would be my intuition, knowing nothing else about the problem. Okay, and then we get some values and plug in the results. So if you plug in all those numbers, you'd get that the delta G for this reaction is minus 6.1 kilojoules per mole. And the delta G naught prime that we started with was minus 24.96 kilojoules per mole. So why don't you actually pause for a second and see, what does that mean in terms of the cell? Like what's going on in the cell? So there's a bunch of things you might say from this, but yeah, think about some of the implications there. So here's a chance to pause. Okay, we're coming out of the pause. These are the things I was thinking about. First of all, that it's favorable to form lactate from pyruvate in this cell. So it's 12 to 1 odds favoring forward to reverse. And I got those 12 to 1 odds by doing e to the minus delta G over RT. That's just what's the probability of a forward reaction over a reverse reaction under these current conditions. But then also that the reaction has equilibrated relative to the standard state, right? So in standard state, it would be 24,000 to 1 odds favoring forward over reverse. And here we're only getting 12 to 1. And what that means is that there's been time for the reaction, that things have equilibrated relative to what they could be. So this reaction is approaching an equilibrium point where we're actually going to start seeing, we actually are already seeing significant back reactions, right? 1 out of every 12 reactions we see will be a backwards reaction. And so this is, approaching, it's getting actually quite close to equilibrium in the cell. Okay, so hopefully that gives you a framework next time you come across a problem like this. So when you see a problem that's about calculating reaction direction, given the set of concentrations of things, you can jump straight into this equation, this delta G equals delta G naught prime plus RT log of Q. And hopefully now you know how to work through one of those problems. So thanks.